Okay, so this is 60 to 62, the second set, and the end of the projectile motion Regents practice. So we have this diagram here, and it states that the path of a stun car driven horizontally off a cliff is represented in the diagram below. After leaving the cliff, the car falls freely to point A in 0.5 seconds. We know this is 0.5 seconds, and to point B in 1 second. So B is 1 second after leaving the cliff. So our first question. Determine the magnitude of the horizontal component of velocity of the car at point B. So we want the horizontal velocity at B. So we have the time. If we look down here, it has the horizontal displacement of 16 meters. So, and it does say a 1-point problem. This is from an older Regents, so on the newer Regents, like the one you'll be taking, this would actually be a 2. So, we have our V vertical. Oh, that's not what I want. Try that one more time. We have our vertical and our horizontal. We're going to split them up. Right now, we're only dealing with the horizontal. So we know from the practice problem that at B, it's at 1 second after it started, and that we're at 16 meters per second, or it's a distance of 16 meters. So our time is equal to 1.0 seconds. Our displacement is equal to 16 meters, and our Vx is equal to, well, that's what we're looking for. So we use our equation, Vx equals dx over t. We sum in our values. And we get a speed of, or velocity of 16 meters per second. You might say, I know that our horizontal velocity is constant throughout. That's a good thing to know. So you can check your answer with another point. So we know at A here, we're moving at 0.5 seconds, and we have displacement of 8. So 8 divided by 1.5, our distance divided by our time to get our velocity, is 8 divided by 1.5, which is also 16. So that's another way to check it. Moving on to 61. So determine the magnitude of vertical velocity of the car at point A. So we're looking at point A. So we know that our time there is 0.5 seconds. We can also determine a couple other things, because we know at the beginning here, the car, when it leaves the cliff, it's going to have 0 initial velocity in the vertical direction. So, set up our chart again. This time we're only going to be dealing with the vertical. We know the time of this trip is 0.5 seconds. We know that our VIY is 0 meters per second. We know our acceleration due to gravity is 9.81 meters per second squared. And you might say, Mr. D, it's actually negative 9.81. And yes, you're right if we're talking about it always is negative 9.81. But that's a vector, okay? We determine direction. We look at the question, and that's why this one's a little tricky. And it's from all the Regents as well. But if we look at it, it says, determine the magnitude of the vertical velocity. So we're only dealing with magnitudes. We're only dealing with the value, not the direction. So we only want values. So actually it is 9.8 because we just want the value of acceleration, not the direction. So basically we're looking for speed. Looking for a scalar. So we can only have magnitudes, no direction. We're still going to use our equation. dFy equals VIY plus AT. We're going to sub in our values. We know this is equal to 0. This is equal to 9.81 times our 0.5 seconds. So our VFY is equal to 4.9 meters per second. We know that this is 16 meters per second. We know this is 4.9. Okay. We look back. Final part. want to know. Calculate the magnitude of the vertical displacement dy for the car from point A to point B. So if we look here, this is what we're looking at. It denotes it right here. So we can determine a couple things. Well, we know when we're going from A to B, the change is from 0.5 seconds to 1 second. Okay? And the difference between that, so our time for this is going to be, because we're going from A to B, we know when we go from A to B, it's 0.5 seconds after we leave to 1 second. So that total time, the difference between those two is 0.5 seconds. We also know that now, from the last one, from 61, that at this point, our Vy is equal to 4.9 meters per second. So that's actually going to be our initial velocity because now we're starting from there. So, we draw our chart again. We're only dealing with the vertical now. We know that our VIY at point A is our answer from 62. It's 4.9 meters per second. We still know our acceleration now, so we're still dealing with magnitude. So we only want the magnitude, not the direction. As 9.81 meters per second squared. We know our time is equal to 0.5 seconds, because that's the time between A and B. We are looking for our displacement in the y direction. If I look at my reference tables, I can use the equation dy equals diy t plus 1/2 at squared. If I sum in, I get 4.9 times 0.5, so 4.9 meters per second, or 0.5 seconds, plus 1/2, the magnitude of our acceleration, and our seconds, or our time, I should say, squared. You do that out, from your calculator, it turns out to be 3.7 meters. So you would circle that, and I found this. So, that's the key difference with this problem is asking for the magnitude. So you have to use it's a little bit different than what we've been dealing with, but you have to use your physics knowledge and the fact that we're dealing with magnitude, we're only dealing with scalars, and we only want the numerical value of, let's say, our velocity and our acceleration due to gravity. So that's how that problem is done. Should be all set.